Hi there, my name is Chance Waswani Msipa. Welcome to another presentation on functions of complex variables. In this particular case, we're looking at computation of residues. As we mentioned before, these are going to be very important tools for our future work. Now, residues of a complex function, or a residue of a complex function, is actually defined by means of its Lorentz series. Like we saw before, we said a residue is the coefficient accompanying the term z minus z0 to the power minus 1. So such coefficient in this case is clearly c sub minus 1. And this is what define what we call a residue of f of z. But this is when we are in the presence of a Lorentz series expansion of f of z. Now, we can now look at a residue at a simple pole. And in this case, we're going to write this way to mean a residue of f of z at z equals to z0 the pole, m equals to 1, to mean that we're dealing with a simple pole. In that case, as you know now, the principal part of the Lorentz series would only have one term, and that term which has got the coefficient c minus 1. Now, to calculate the residue, to get the residue here, we notice that if we multiply this expression, both sides, by z minus z0, would obtain the following expression, which is z minus z0 times fz, and that results in a kind of isolation of c sub minus 1. Now, our task is to find a way of computing, given a function, find a way of computing a residue. Now, what you see at this stage, after isolating c sub minus 1 by multiplying both sides by z minus 1, is that if now we let z be close to z0, otherwise z tends to z0 as we want, then these terms would become negligible as the change as z is going closer and closer to the 0. So that idea introduces the idea of a limit. In this case, if we now apply the limit as z is going to z0 of let's say z minus z0 times f of z, and apply that limit both sides here. In this case, this difference z minus z0 is going to be negligible. In this case, we're talking about here change in z is going to tend to 0, and then the terms above c minus c1 will also tend to 0. Then the limit here will be c minus 1, because c minus 1 in this expression, c sub minus 1 in this expression does not have the term z minus z0. Then this discussion results in a formula for computing a residue, which is given this way. We write res in brackets of f of z, z equals to z0 order 1. That will be the limit of this kind of expression. Is going to give us what we call what we have as our residue. Now, looking at this example, let's say in this case the simple pole in this case is z equals to -4, because z equal to 0 here is a double pole, and we already looked at that. So getting a residue at z equal to -4, we try the following. Res of f of z, z equals to -4, and the m equals to 1. I'll advise you to write this way very clearly and communicating what you want. But for the case m is equal to 1, we may leave this part and just write residue of fz, semicolon there, z equals to 4. Once we don't see any m there, we'll assume that this is a simple pole. Then according to the formula, we'll then multiply the function by z -4, -4, which will be multiplying z plus 4 multiplying z plus 1 over z squared by z plus 4. So we can see here we've got z plus 4 in the numerator and the denominator, which means they're going to simplify to 1. Then we're left with z plus 1 over z squared. For the computation, then we'd write limit as z approaches -4 of the resulting expression here, which is z plus 1 over z squared. Now, since this expression is defined at z equal to -4, then we can compute the limit by directly substituting z, which gives us -4 plus 1 over -4 squared, which simplifies to -3 over 16. So in this case, -3 over 16 is our residue for the given function f of z at a simple pole z equals to -4. Now, looking at poles of order m greater or equal to 2, starting with 2, we know that the Lorentz series will have 1, 2 terms in the principal part. Now, we want to calculate to find our residue, or to see how we can arrive at c minus 1, which is our residue. Now, trying to take advantage of what we've seen before, we managed to isolate c minus 1. We can multiply again this expression by z minus z0 to the power 2 to obtain this kind of expression. And in this case, we've managed to isolate only c sub minus 2. And we observe that if we differentiate this expression, this c is going to be 0, and the derivative here is going to give us c minus 1, which is actually going to isolate our residue. This is what we do here. We differentiate both sides of this expression. We get 0 there, and the derivative of this expression in brackets is 1 multiplied by c, or c minus sub 1, our residue. Then the rest, using power rule, gives us the following terms. Please double check my calculations there. There might be some numerical errors, which is normal. Now, moving forward, now that our C and our residue has been isolated, we can still consider exactly the same idea. So here it's supposed to be Z0, that this change in Z approaches 0, and that again introduces the idea of a limit. Now, if we now apply limit on both sides here, we would say limit at Z is going to Z0 of dz of Z minus Z0 squared multiplied by Fz. At this moment here, there's not much we can do here, otherwise we can just have this as a placeholder of the expression, because we cannot differentiate here. We calculate the limit on both sides, and as we calculate the limit on both sides, delta z tending to 0, we'll see that the limit here is going to be c sub minus 1, which is our residue. Now, this gives us the following. Now we can say the residue at the multiple point pole z equals z0 of order 2 can be given by this formula. So again, we can now look at this example. In this case now, a pole of order 2 here is z equals to 0. So doing this, what you're supposed to do is you're supposed to multiply the function by z minus 0 squared, which is actually going to give us z squared. So multiplying will say z squared multiplied by the function is z plus 1 over z squared multiplied by z plus 4. So if we multiply, we see that these two simplify to 1. Then now we can write res for residue of f of z at z equals to 0, m equals to 2, meaning it's a double pole, equals to the limit of the first derivative with respect to z of the resulting expression here, which is z plus 1 over z plus 4. So here first we need to differentiate the expression in brackets before we can compute the limit. So we write here limit as z is going to 0 of differentiating, applying the quotient rule here, we're going to have z plus 4 whole squared multiplied all squared, and the numerator will be 1 as the derivative of the numerator multiplied by the denominator z plus 4 minus the derivative of z plus 4, which is 1, multiplied by the numerator z plus 1. Now computing the limit, or first of all, say simplifying the numerator here, we've got z minus z, which give us 0. Then 4 minus 1 could give us 3. Then we've got a limit is z is going to 0 of 3 over z plus 4 all squared. Now since this expression is defined as z equals to 0, then we compute the limit by direct substitution by z equal to 0, which gives us 3 over 4. 4 is resulting from 4 plus 0 all squared, giving us 3 over 16. In this case now, our residue of given f of z at double pole z equals to 0 will be 3 over 16. I hope you've seen how this formula has been applied here to compute residue, and that you're going to be able to do some simple practice following this example. Now, considering m equals to 3, we know again that the Lorentz series is going to have 3 terms on the principal part, then multiplying by z minus z0 to the power 3 on both sides of this expression. Sorry, here it's supposed to be z0. We get an expression like this, and we see that we only have c minus c sub minus 3 isolated, but from what you've seen, we need to isolate c sub 1. So we differentiate by that. C derivative of c sub 3 0, then we get c sub 2 isolated, and now it becomes clear that if you differentiate for the second time, the derivative here is going to be 1, then you get c sub 1 somehow isolated by accompanied by this coefficient 1 times 2. I just decided to write 1 times 2 here for you to be able to observe what I would like you to observe at the end. So don't worry about it for now, because it doesn't necessarily change this derivative, which is 2 times c times 1. Then differentiating for the second time to isolate that term with c, we get c 1 times 2 times c1 this way. Now from here again, we can now try to use that idea of calculating limit as delta z, which is z minus z1, is tending to 0. Now, if we do that calculation of limit, this is what we get. We calculate this limit to get 1 times 2 times c1, but in this case, our residue is not 1 times 2 times c sub 1, but is c, which means we need to make here c sub minus 1 the subjective formula. Now, for that, what you can do is to divide both sides by 1 times 2, which in this case is going to be 1 over 1 times 2 multiplied by the limit z going to z0 of d2 over dz2 of z minus z0 power 3 times z f of z. That will be equal to c sub 1. Now, one thing which you should notice here now is that the number of times we differentiated here is 2 and the 2, and this 2 is actually equals to 3 minus 1. In the previous discussion for a simple pole, we noticed that we differentiated once and then we had a derivative of order 1, and again the 1 was equals to 2 minus 1, and there is no coefficient here, but if we want to be in agreement with what we've seen here, we can check that there is a coefficient here. In this case is 1 over 2 minus 1 factorial, which resonate with what we have here. We have 1 times 2, which is actually 2 factorial, which is the same thing as 3 minus 1 factorial. This kind of discussion helps us to sort of generalize and get an idea of what we'll do if the pole Z0 is of order m greater than 2. And then generalizing this, I repeat, you need to notice that the differentiation here is done to the order 3 minus 1, the pole is of order 3. And the factorial which is coming here is a factorial which is equals to factorial of 2, 2 being equals to 3 minus 1. So generalizing that to any pole of order m, we've got the following formula. First of all, this is for order 2. For order 3, we've got this. Then taking that to a general form, we have the formula looking like this. We have to be able to read the formula back to ourselves. We're talking about here residue of a function f of z at z equals to z0, order m. Then we are going to calculate this by reading from the innermost of this formula. We first need to multiply fz by z minus z0 to the power m. After we've multiplied, we differentiate number of times equals to m less 1. This is what it's saying there. Then we calculate the limit, and after calculating the limit, we multiply that by 1 over the factorial m minus 1. That would be a way of computing residues of order m. Now, to take this further, hoping that you understand what is happening in this formula, I would invite you to go and attempt the following exercises. Determine the residues for the following functions at each of the poles. As you can see, some poles here are simple, some are repeated, like 2 years repeated, and the 0 years repeated 4 times. And here you've got to see what you need to do before you can decide exactly which are the poles. Otherwise, at this point, I hope the formula for computing residues, be they simple poles, double poles, and repeated 3 times or more, you understand how to compute such. But of course, I will need to give you some further kind of tutorial for you to master this kind of work. Otherwise, for now, thank you for listening. Meet you during the future discussions of this topic.